Chapter 6 deals with thermochemistry, energy flow, and chemical change. So thermochemistry is the changes in the heat of a chemical reaction. So we're going to look at a lot of chemical reactions and talk about the changes in heat that occur with those chemical reactions. So energy is nothing more than the capacity to do work. And you think about this in your everyday life. If you think about being low energy, it's hard to do work when you don't have a lot of energy. And in this chapter, we're going to deal largely with thermal energy. And thermal energy is the energy associated with the random motion of atoms and molecules. We have some other kinds of energy that are shown here: radiant, chemical, nuclear, and potential. No matter what the form of energy or the situation, when energy is transferred from one object to another, it appears as work and/or heat. So heat is the transfer of thermal energy between two bodies that are at different temperatures. One thing that is important to remember is that heat is always going to flow from a hot body into a cold body. So it will always flow from hot to cold. Temperature is just a measure of thermal energy. Now, temperature doesn't equal thermal energy because the units of energy are joules, whereas temperature, we're going to be dealing with Kelvin. So you can see that thermal energy and temperature can't be equal, but temperature, again, is nothing more than a way to measure thermal energy. So thermochemistry is the study of the heat change of chemical reactions. And like I said, we're going to look at a lot of chemical reactions throughout this chapter and discuss the changes in heat associated with those chemical reactions. Before we can really get into thermochemistry, we have to define what we call the system and the surroundings. So the system is the part of the universe on which our attention is focused. This is going to be the reaction itself. The surroundings is the rest of the universe. So practically speaking, we're going to look at the surroundings that are coming into direct contact with our system. So things like the reaction flask. So remember, the universe does not include the entire universe, just the system and the surroundings. If you're doing a chemical reaction down here on planet Earth, it's not going to have a big effect on what's going on in Pluto, for example. So remember, the universe is just what's in proximity to our system. When we study a chemical reaction, we have to consider the system to be the reactants and products. So this is our chemical reaction. The surroundings are mainly the reaction media, so the solvent that the reaction is being performed in, the vessel, whether it's a beaker or a test tube or some kind of round bottom flask in which the reaction takes place, plus the air or other material that comes into close contact. So the universe is in fact very close to our reaction. So here's a couple of definitions that you have to be clear on. So you have to know what an exothermic process is and what an endothermic process is. An exothermic process is any process that gives off heat, or another way of putting that is saying it transfers thermal energy from the system into the surroundings. And the reaction that I have shown here is hydrogen gas plus oxygen, which gives you water plus energy. Now this is a combustion reaction. You might remember this reaction from the Hindenburg, right? Hydrogen burned in the presence of oxygen to produce water, but it also produced a lot of energy. And the way I think about this is the exo, I think of like the word exit, which means leaving. So energy is leaving the system. Here's another example. This isn't a chemical reaction. This is just a phase change. When I take water in the gaseous state, so we call this steam, and I convert this into water, so it's undergoing condensation. Not only does it condense, but it releases energy. And if you've ever been burned by steam, you're aware of this, because what happens is when steam hits your skin, it condenses, right? Because your body temperature is below 100 degrees Celsius. It's around 37 degrees Celsius. So when that steam condenses into water in the liquid form, it releases a lot of energy. And that's what causes a burn when your skin is exposed to steam. An endothermic process is any process in which heat has to be supplied to the system from the surroundings. Take, for example, this decomposition reaction that I have shown here. So if you have 2 moles of mercuric oxide, it decomposes to give you 2 moles of mercury plus oxygen, but it requires energy being put into the system. So energy can be regarded as a reactant in this case. The same thing occurs in this phase change down here. So if I have water in the solid phase, that's ice. And if I'm melting it into liquid water, it's going to take energy. So I'm going to have to put energy into that process. So again, you need to know what an exothermic process is and what an endothermic process is. This slide is nothing more than a schematic of exothermic and endothermic processes like we saw on the previous slide. So for both of these reactions, I have energy going up this way, like this for both of them. So these are two different processes. So if I take a look at the one on the left, I'm taking hydrogen gas and I'm combining it with oxygen gas and I'm forming water. Now that's a combustion reaction like I just mentioned on the last slide. And what happens is not only do I form the product, water, but I'm giving off heat to the system. So you form the product plus you form heat. But where does that heat go? It's going to go from the system into the surroundings. Conversely, if I take a look at this reaction over here, where I take mercuric oxide and it undergoes decomposition to produce mercury and oxygen, this reaction has to absorb heat from the system. So that makes it an endothermic reaction. It's absorbing heat from the surroundings into the system. So to summarize, an exothermic reaction is one where heat is given off by the system to the surroundings. An endothermic reaction is one where heat is absorbed by the system from the surroundings. Thermochemistry, which is the study of how heat is exchanged in chemical reactions, is only a small part of a much broader subject that we call thermodynamics. Thermodynamics is the scientific study of the interconversion between heat and other kinds of energy. And in thermodynamics, we have something that we call state functions. And state functions are properties that are determined by the state of the system, regardless of how that condition was achieved. Examples of state function include things like energy, pressure, volume, and temperature. And if you take a look at all of these formulas that I have over here, you can probably draw a conclusion pretty quick. That if I have a state function x and I want to determine the change in x, so the change in a state function, that's going to be equal to the final state of my state function subtract the initial state of my state function. So again, that applies to energy, pressure, volume, and temperature. Now if I take a look at this picture that's shown down here, I have two hikers at the top of a mountain. It says down below that the potential energy of hiker 1 and hiker 2 is the same even though they took different paths. And the reason why is because potential energy depends on height. Now they're both at the same height. But what's different is the path that they took to get there. Now again, the potential energy is the same for both of these hikers because they're at the same height and my potential energy is related to that height. But if I think about those paths that they took to get there, did they use the same amount of work or did they require the same amount of work to get to that height or to that potential energy? The answer is no. And we're going to see this later that work is not a state function. So W, which we use for work, is not a state function. And I have this shown in a slide later on that you cannot calculate delta W. It doesn't work that way because, no pun intended, work is not a state function. This brings us to the next slide, which discusses the first law of thermodynamics. It's really the only law that we're going to look at in this chapter. And the first law of thermodynamics states that energy can be converted from one form to another, but it can't be created or destroyed. So what does that mean? That means if I look at the change in energy of my system, my reaction, and the change of energy in the surroundings, right? Because energy is going to flow from one to the other, or vice versa. The sum of those changes in energy should be zero. So let's think about it in terms of what I have written here. So I've just rearranged the formula to be delta E of the system is equal to the minus or the opposite of the delta E of the surroundings. Let's take, for example, a reaction where we're losing energy. If energy is being lost in our reaction, our system, where is that energy going? It's going into the surroundings. So if my system is losing energy, it's going to be gained by the surroundings, and vice versa. So if I take a look at this reaction down here, this molecule C3H8, this is the molecular formula for propane. So when I take propane and I combine it with oxygen, I get carbon dioxide and water, but not only that, I produce heat. And if you've ever operated a barbecue, you're fully aware of that. So this is an exothermic chemical reaction. Chemical energy that's being lost by the combustion, well, where is that energy being lost to? it's being gained by the surroundings. So again, this formula is going to be very important as we move forward, that the change in energy of the system is going to be the opposite in sign of the change in energy of the surroundings. Another way to express the first law of thermodynamics is to use this equation that I have on the top left, that delta E is equal to Q plus W. Now delta E is the change in internal energy of the system. Q is the heat exchange between the system and the surroundings. So whether the heat is leaving the system or whether it's leaving the surroundings and going into the system. W, which I mentioned earlier, is the work done on or by the system. And we can define W as being equal to minus pressure times delta V. So if you think about what kinds of work can be done by a chemical reaction, well, really the only kind of work that can occur via a chemical reaction is going to be either expansion of a gas or contraction of that gas. So if you think about a reaction where I'm producing gas, what's going to happen is that gas is going to push back against the atmosphere and it's going to do some kind of work. And we'll look at that in more detail. So if I think about expansion of a gas, okay? So if I think about a gas expanding, what's my delta V going to be equal to? Well, it's going to be a positive number because the final volume will be greater than the initial volume in expansion. So based off of that, if I have just gas expansion, and I'm just thinking about this specific case when a gas expands, well, my work is going to be equal to minus the pressure. Now the pressure, we're always going to be looking at positive pressures. We're not going to be talking about doing reactions or chemistry at negative pressures. So that means my pressure value is going to be a positive number. And my delta V, which we already decided, is going to be a positive number. So that means that my work is going to be a negative number when I have a gas expanding. And if I think about that, which is this scenario here, that work is being done by the system on the surroundings. What does that mean? That means that when the gas is expanding, it's pushing back against the system, right? Pushing back against the surroundings. Because the system is the chemical reaction, and if the chemical reaction is producing a gas or it's expanding, it's pushing against. So the way I think about it is that work is being done by the system, so work is leaving the system. So I think about that in terms of a negative sign. Conversely, if work is being done on the system by the surroundings, you can think about the system as taking in work from or having work performed on it by the surroundings, and the sign changes to positive. In terms of my Q, my heat, when I have heat that's being absorbed by the system from the surroundings, we call that an endothermic reaction. So that means that heat is coming in from the surroundings. So endo, it's coming into, entering. Whereas if heat is being absorbed by the surroundings from the system, that means that the system is putting heat out into the surroundings. So the heat is leaving the system. So that's why I think it's easy to think of that in terms of negative, right? If it's losing the heat energy into the surroundings. So you need to be fully cognizant of the signs for all of these scenarios and when to apply them. So let's take a look at what the sign of delta E would be based off of my Q and W. And we know this formula from the last slide that delta E is equal to heat plus work. Let's take a look. If my heat value is positive and my work value is positive, well then my change in energy has to be positive. If my heat value is positive and my work value is negative, well, the change in energy, the delta E, is going to depend on the relative sizes of the heat and the work. Also, same type scenario, if my heat is negative and my work is positive, well, the same thing. What the sign of delta E will be is going to depend on the relative sizes of Q and W. Then if I have both negative values for my heat and my work, well, of course, in that case, my delta E is going to be negative. So to summarize, for Q, when I have a positive Q value, this means that the system is taking on heat or gains heat. When my Q is negative, that means that the system is releasing heat into the surroundings. When my W is positive, that means that work is being done on the system by the surroundings. And when my W is negative, like in the case of gas expansion, that means that work is being done by the system on the surroundings. The way that we define work in physics is that work is equal to force times distance. So if you've ever studied physics before, you've probably seen this formula. But the way that we define work in chemistry, as we said before, is that work is going to be equal to minus P delta V. And you might be wondering, well, how do force times distance and minus P delta V, how are they related to each other? Well, if I just think about what P is, what pressure is force per unit area. Now, if I take a distance and I call that D, well, area is going to be D squared, for example. So that means that my pressure could be defined as force per unit area, or F over D squared. Now, for my volume, I could define that as D cubed. So here's my volume. So when I multiply my force times my distance, so when I multiply my pressure by my volume, I end up with force times distance. So now you can see the relationship between force times distance and pressure volume work. Now, if I take a look at this scenario down here, this is a specific reaction. So there's some kind of gas in here, this green gas that's inside here. And what's happening, we have the initial volume of the gas, but you can see that over the course of the reaction, the gas is expanding against this external pressure. So some kind of pressure. So if the gas is expanding as I go from left to right, my delta V is going to be a positive number. And they've demonstrated that for us here. Now, if my delta V is a positive number, another way of saying that is that delta V is greater than 0. Now, again, I told you that pressure will always be a positive term. So if I have minus P times delta V, that's going to be minus times a positive and a positive, which is going to give me a number less than 0, or a negative number. And since work is equal to minus P delta V, that means that my work in this specific case that's shown down here, my work will be less than 0. Does that make sense? Well, yes, it does, because we said that when work was being done by the system on the surroundings, the W value was negative. It's also important to know that work is not a state function. Now, I mentioned this earlier, but when you're calculating the change in work, you can't just say delta W is equal to work final minus work initial. Cannot do this. Now, if you think about this in terms of work, let's say you wanted to, pick up, a 10-pound weight and put it on top of a table. Well, there's some work involved in picking that weight up and putting it on the table. So it went from, let's say, the floor to the top of the table. Okay, so it took you a certain amount of work, force times distance. But what if I picked up that weight and I ran around the block 2 times, and then I came and I put it on top of the table? It still get to the same place, but there was a different amount of work associated with it. So therefore, you can see that work is not a state function. Let's take a look at a sample problem, problem 6.1. It says a certain gas expands in volume from 2 to 6 liters at constant temperature. Calculate the work done by the gas if it expands against a vacuum or against a constant pressure at 1.2 atmospheres. Let's start by calculating delta V. Delta V, volume is a state function, so we can say delta V is equal to the final volume minus the initial volume. So that's going to be equal to 6.0 liters minus 2.0 liters, which gives us a delta V of 4.0 liters. Now it's asking us to calculate the work done by the gas if it expands against a vacuum. Now, if we're in a vacuum, then our external pressure is equal to 0 atmospheres. So this one doesn't take a lot of thought to solve to the final answer. To get to the final answer, my work is equal to minus P delta V. So my work is going to be equal to minus 0 atmospheres times my delta V, which is 4.0 liters. And I'm sure you're way ahead of me already. That work is going to be equal to 0 atmospheres liters. And I don't even have to do a conversion. It's going to be equal to 0 joules. So no work was done because the gas didn't have to expand against any kind of external pressure. In B, it says that the gas is expanding against a constant pressure of 1.2 atmospheres. So my pressure is equal to 1.2 atmospheres. So if I use my formula, work is equal to minus P delta V, and I plug everything in here, we'll put minus 1.2 atmospheres multiplied by my delta V, which is 4.0 liters. When I plug that into my calculator, I end up with minus 4.8 atmospheres liters. Now you might remember that I showed you a conversion factor a few slides ago, which was that 1 atmosphere liter is equal to 101.325 joules. And we're going to use that to determine how many joules of work was done. So let's do that. So we have minus 4.8 atmospheres liters times 1 atmosphere liter on my denominator is equal to 101.325 joules. My atmospheres and liters cancel out, and I end up with minus 4.9 times 10 to the power of 2 joules. So there's the amount of work that I did. Now, if you think about this in terms of the sign, does it make sense? Yes, because work is being done by the system against or on the surroundings, right? Because the gas is expanding.